the actual power generation, considering motor losses, will be less than the generator's nameplate rating. In this case, a 10 kilowatt generator driven by an 18 horsepower motor will not deliver a full 10 kilowatts to a load. The key factor is the motor's efficiency. Motors aren't perfectly efficient. Some of the input power is lost as heat due to factors like friction in bearings, winding resistance in the motor's coils, and coal losses in the motor's iron. This power loss reduces the amount of mechanical power the motor can deliver to the generator's rotor, which in turn reduces the electrical power output from the generator. Motor efficiency is usually expressed as a percentage. A typical motor efficiency might be around 80 to 90%, but this varies depending on the motor's design, size, and load. To calculate the approximate power loss, we can consider a range. Let's assume an efficiency of 80%. This means that for every 100 watts of electrical power consumed by the motor, only 80 watts are converted into mechanical power. The remaining 20 watts are lost as heat. If the motor is driving a 10 kilowatt generator, and we assume the motor is perfectly matched to the generator's requirements, we could initially think the motor needs to provide 10 kilowatts of mechanical power. However, because of the motor's inefficiency, the electrical input power to the motor will need to be higher than 10 kilowatts. With an 80% efficiency, the electrical input to the motor would be 10 kilowatts divided by 0.80, which equals 12.5 kilowatts. The difference between the 12.5 kilowatt input and the 10 kilowatt output represents the power loss in the motor, which is 2.5 kilowatts in this example. In this scenario, the actual power delivered by the generator to the school would be approximately 10 kilowatts, which is its rated output. The motor's inefficiency affects how much power the motor draws from its power source, not the generator's rated output. The motor's 18 horsepower rating is a measure of its mechanical power output capability. 1 horsepower is approximately equal to 746 watts. Therefore, 18 horsepower is roughly equivalent to 13.4 kilowatts. This doesn't mean the generator is producing 13.4 kilowatts. It simply indicates the motor's power capacity. The generator's output is limited by its design and is stated as 10 kilowatts. The 18 horsepower motor provides sufficient power to drive the 10 kilowatt generator, even considering the motor's losses. In practice, the exact power loss will depend on several factors: the motor's actual efficiency at its operating load, the generator's efficiency, and any other mechanical losses in the system. It's also important to consider the power factor of the load connected to the generator. Power factor is a measure of how effectively electrical power is being used. A lower power factor means more current is required to deliver the same amount of real power, which can lead to increased losses in the system. To accurately determine the actual power delivered to the school, it would be necessary to measure the generator's output voltage and current, as well as the power factor of the load. This would provide a more precise understanding of the system's overall efficiency. So, to reiterate, the generator itself is producing 10 kilowatts, which is its rated output. However, due to the motor's inefficiency, the power source supplying the motor needs to provide more than 10 kilowatts. Some of that power is lost as heat within the motor. When considering the actual power available for use at the school, it's essential to understand this distinction between the generator's rated output and the impact of motor losses on the overall system.